The goal of experiment 8 is to find the molar mass of a volatile liquid. So we have an unknown liquid that we are going to determine its molar mass by turning it into a gas. You need to complete for this lab the quiz for experiment 8. You're going to turn in the Excel file that is available to you on Canvas, and you're going to upload it to Canvas once you've completed the calculations. You are also going to complete your lab notebook and upload a PDF of your notebook into Canvas as well. What does volatile mean? If we're going to find the molar mass of a volatile liquid, we need to know what volatile means. And so volatile means that it is easily vaporizable. It transitions or it turns into a gas very easily. And we do that by adding heat. By turning this into a gas, we can use the ideal gas law to help us figure out the molar mass. So what is the ideal gas law? What's the equation? The equation is the pressure of the gas times the volume is equal to the number of moles times R, which is a constant, times the temperature of that gas. Now, if we want to find the molar mass, we need to know what its units are. So what units does molar mass have? It has the units of grams per mole. And so we're going to rearrange the ideal gas equation in order to calculate the grams per mole of the gas, or the molar mass. All right, so the way that we come up with this equation, and this is shown in your lab manual as well, we start with our grams per mole, and if we rearrange this equation and solve for moles, we end up with the grams over the molar mass. We can substitute that in for the moles in our ideal gas equation. So now we have grams over molar mass, where N used to be. And we can solve the equation for the molar mass. And using this equation, it's the grams of the gas times R times the temperature divided by PV. All right, so what do we need to measure in order to find our molar mass? There's some measurements that we need to take. We need to measure the temperature of the vapor, so we need to know it in Celsius, and then we can convert it to Kelvin, because using this equation, it has to be in Kelvin. And so to measure the degrees Celsius, we measure the temperature of the water, we measure the temperature of the vapor above the water, and we average those two temperatures. We also have to measure the volume. So we're going to put it in a 125 milliliter Erlenmeyer flask, but that just means that it contains 125 milliliters, not that the flask itself, the whole volume is 125. So the way we do that is we use a graduated cylinder. We add water until it is completely full to the brim and record the volume off of our graduated cylinder. We also need to know the pressure. And so this inside of our flask, the 125 milliliter Erlenmeyer flask, we're going to cap it, but it is still open to the atmosphere. The gas can escape. So we are going to use the atmospheric pressure in white water to measure that's going to be equal to the pressure of the gas. And we do need to convert this from millimeters of mercury into atmospheres so we have the proper volume. R is our ideal gas constant. It's 0.08205.821 if we want a few more significant figures. Most of the time, we end up rounding this number to 0.08206. And if you notice the units on this constant, these are the units that need to that our other measurements need to be in. All right. In order to find to do the procedure for a volatile gas, we have to find the volume of the flask, and then we flame dry the flask to make sure that it is completely dry and there's no water in our empty mass. We collect all the materials and supplies, so there's some pieces of aluminum foil and wire and a rubber band. We wipe down the outside of the flask to make sure that there's no carbon from that flame. And we will do work on this in the hood. The reason we work on it in the hood is because as we're volatilizing the gas, as we're turning it into a gas, some of it is escaping from our flask and those vapors enter the room. With enough people doing this experiment, when the vapors enter the room, it can get pretty stinky, and we don't want to expose people to all the vapors of the unknowns. Once our flask is dry, we're going to weigh it on the analytical balances. And we do want to make sure that that includes the wire cap or the wire and the foil cap. We're going to add half of our unknown liquid, and the reason we add half is because we're going to run 2 different trials. We put the smallest piece of aluminum foil over the flask and tighten it with the wire. Now our goal is to make a watertight seal, but not a gas-tight seal. We're going to assemble our apparatus. So we're going to add our flask with a little bit of liquid down in the corner. That goes into a larger beaker with some boiling chips. And we heat this and watch very carefully until all of that liquid in the flask has completely vaporized. As soon as we notice that it is vaporized, we want to remove it from the flask. So just before it is all vaporized, we want to take the temperature of the water that's surrounding the flask and the temperature of the vapor that's above the flask in order to find the temperature inside the flask. We're gonna, once we remove the Erlenmeyer flask from the apparatus or from the beaker, we're going to, once it's cool enough, take that rubber band off, take the outside piece of aluminum foil, and we're going to leave the smallest piece of aluminum foil with the wire in order to make sure that we're not allowing any of the gas that completely fills the container to escape. Once that's condensed and it's cool, we can wipe down the outside and we want to weigh it on the analytical balance. Now we do need to wait until it's cool to weigh because hot objects do weigh more than cool objects. And so it does need to be room temperature to get the most accurate mass. Once we've done that, we can repeat that entire procedure again to do the second trial of our experiment.